Okay, so this is the outline of today's session, and we have a lot on the list to do today. I want you to do the first two because that will take time, and especially if you don't have the example data set we created last week. You have to use Toolbox to download it and process it. And on here, I had my processed data saved from last week. So for me, I just upload that data to Toolbox easily. But if you don't have that, let's go through over that and let the computer to run in the background, and then we move to the rest of the items in the list. So first, we do have some update on the package. So I will copy this code and found my current working directory. So my working folder right now is under my username, then documents, MATLAB. So this folder, and in this folder I had previously and installed my package here. So that's the place I want to paste my this quick installation code here. So to let the program to download the package and overwrite the current folder. If you are in current folder inside, you will install another version which under the older version. That's what we want to avoid. We want to overwrite the old one.
So just to clarify,
Mm-hmm.
you just need to remove your name and put in our username that's...
No, you should have your own username. Yes, you should, yeah. The only difference is make sure you know, okay, it should be in this folder.
Okay.
Yeah. So I copied the installation code and put in here, and then after run this in the command line, I got this Toolbox installed message. That means this Toolbox, everything under this folder had been overwritten. Yes?
Little confusion, like you mean like instead like on that unzip thing, we have to write our name, or where do we have to write our path? Is it on that unzip thing, or is it on the pathway?
Oh, this unzip thing, you mean here? This?
Yeah, you have your name, right? James David I.
Yeah, so you should have your own computer account username. So normally, by default, you should be here. Yeah, that's my username. Then on your computer, you should have your own version. Yeah, so if you see, okay, yourself is here, then you can run this code.
My question is like you have like VIBS.com, that should not be changed, right? That should remain the same, right?
Yeah, everything else should remain the same because that's other files or you previously prepared. Yeah.
So I changed my username, but I'm still getting an error.
Mm-hmm.
I think they got confused with the GitHub URL. So we are actually getting it from the repository, your repository. They got confused as to...
Oh, this. So keep this original. Yeah, I'm sorry.
I just wasn't clear.
Yeah, because the source code I put under my name over there. Yeah. Yes, not that part. Yeah. we prepare this data set because at the end, we will try to do this DE analysis, differential expression analysis. Once we finish, almost done with today. So we prepare last week the data set. That data set, we have 2 samples. The 2 samples from a skin. And if you remember, you can Google this accession number. You should find that record in geodatabase. Okay, with these 2 numbers, 2 accession numbers. We can copy this and be ready to import the data. So what we have to do is just run this program here. Yeah, the latest version, I will change a little bit the behavior of the program. I put an X there. You can use that. Should have a same behavior, but a slightly different procedures. In this case, we can see I want to import data from the geo session number. Can you see it? Okay. In here, I put that 2 numbers in to allow the program to download from the web page. You also have this small example accession number on this label, and if you want to use that one, it's okay, fine. It's a smaller data set.
But if you save the mat file, you shouldn't back time while you open it.
You should still have it. Yeah. Yeah. If you.
I think last time I said workplace, but I don't.
Yeah. If you cannot find it, you have to redo it. Oh. Yeah. Because workplace is just in the memory, not in the hard drive. So you come back this week, it's gone. So it's better to save in the MAT file. So I saved in MAT file, so I suppose I should be able to.
Yeah, I didn't save.
I shouldn't. I shouldn't need to do this again, but I just show you the procedure. Well, I just let this program to run in its background, and then I just start another session of MATLAB. I will be independent to separate the session. And so I just run this program again. So here I have another interface. This computer, this desktop should be strong enough to have multiple sessions. So here we can play with these random numbers. And until the other side finished, we save the file. Okay, as I said, if you look at the document RND, so RND is a built-in function in MATLAB. The whole purpose of this function is to generate a random number. This is between 0 and 1. Okay. By the way, this is not a truly random number. It's simulated by machine. Okay. So this random number is simulated by a random number generator algorithm. So if I do a random, the first number on my screen, 0.8146147, if you see the same number on your machine, don't feel surprised, because this is a machine generated, simulated number. Okay. It's just like you have a large pool and several millions of random number here, and this random select the first one. Gave you the first one if you ask first one. Okay. Do we have the same number generated here? Yeah. Because this is, we start from the random number generated seed. This seed number will define where you start to draw your random number from this large pool, basically. Okay, so if you start from the same seed number, by default, we will get the same random number. So if you run this random number generator and the shutdown machine, run that again, no matter how many times you open your MATLAB session, you run this series random number, they're all the same. So don't be confused with this pseudo number generator. It's not a true random number. Be aware of this. What you can do is you change the seed number. You have to change the random generator seed in order to get another completely different series of the random number. And also recently I received some advertisement from some company say, I want to sell you a random number generator machine. And they are physical random number generator. In that case, you generate a real random number. They use quantum computers to do that. So the random quantum computer is really good to generate a random number in this case. Okay, so you can generate a lot. See, I have a render. I will generate 1,000 of them. So this will give you a long list by column, and that's 1,000 random number. And it's continuous. It's not 1, 2, 3. Okay, so it's between 0, 1, any place. So if you receive a list of this, so we see I receive a variable that's observation. So what you can do first is to run a histogram, for example, histogram. You put X in here. All right. The purpose of this is you want to put the values into the bins and see which bin you have a highest number fall into that bin. That means in your random number, in this variable, you have a high frequency to observe values in that small bin compared to others. However, in our case, this is supposed to be uniformly distributed. So this 1,000 random number should be uniformly across all the bins, okay, by default, because we are using the uniformly distributed random number generator. If this number is not enough, so you see some variability. So by chance, this bin from 0.1 to 0.2 values have 120, a little bit more, 27. to make this even close to the theoretical prediction, so what you can do is increase the number of the random numbers. Say, I want to do 50,000 rather than 1,000. So I just follow that distribution and generate more, and then look at its distribution again. So this histogram is a distribution, basically, let you know, okay, what it looks like. Where distributed more for those random values in which bin. All right? Now I'm going to switch to my, yes, I have this from the other session. I want to process it and using 3D. So that's this human skin sample. So yeah, I just leave that. Let it run in the background. Okay, let's check another random number generator function. This time is random n, okay? You can read its documentation and you see the difference, the definition. Now I want to know whether you get the same value as I get from here. Okay, it's different. So our machine has been shuffled somehow. The random number seed changed. Okay. But if you want to get the same value by this simulation, what we can do, we can reset all our computers using same random number generator seed. So what I can do is to call a function called RNG. Yeah, my computer is frozen. See, so let's set up into today's date 2/8. So this function allows you to reset your random number generator seed. If we all set our computer random number generator seed to the same number, the next random number we generate should be the same. So I reset my machine and then run this. Again. What's the number you get on your machine? The same. Okay, that's right. Correct. Supposed to be the same. That's why in some program you may say, okay, I want to preset the random number seed. Okay, let's run generate 50,000 of this. Remember, this time I use random normal distribution random number generator rather than the without n is a uniformly distributed number. Now you can draw this histogram again, and you will see the normal distribution is curve. Okay, we get this, right? So next, in our class, we mentioned the negative binomial distribution. So we are going to use examples to use this random generator of this to generate. So the function we are going to use is called NBIN RND, okay? Negative binomial random number. So in this case, if you don't give any input variable, so if you don't give R value R and P, then you should get error message, because without any parameter, you cannot define the distribution of this this function. So you need, in this light blue example, you need a value 7 and 0.3. These two values to define negative binomial random number, the underlying distribution. From that distribution, the random number will pop up. So negative binomial rand, okay? Remember, I can do this random number n without any parameters, because by default, I know the average is 0 and the variance is 1. But for this distribution, I cannot do it because I need at least 2 input variables to define the distribution, what the shape is. So I will use example 7 and 0.3 in our PowerPoint slide. So once I give this 2, I can generate number, okay? What's the difference? The first difference you will see is it generate integers, right? Yeah, every time you have different, yeah. Every time you have a different, this pop out from that distribution. The distribution looks like this blue, light blue curve. If you give different parameters, say this purple, dark purple, then if you put 1 and 0.2, you define a different distribution. Then from that distribution, you generate those random number. And this is a discrete distribution, so you get integers. Yeah, that's from my another background. I remember we need to remove some gene, because those genes are the spike in the, yeah. But anyway, so I will do this later. I think what we can do is we just remove all the genes without approved symbol. That's easy. So you just keep this human genes has been well documented. All the genes should have a name. This should be my clean data, so I can save as a mat file. Okay.
What is the proof?
Yeah. So for the human gene, there's gene names.
Remove 3,000.
Yeah. Yeah, it's okay. So for human, there's a consortium. People control the gene name. So that's the organization. If it's a well-documented gene, you should have a good name. Otherwise, you may have a name something like open reading frame 13.5. So those genes, even though later you found some differential expression pattern, for example, you cannot explain them biologically. So for easy interpretation, that we can just remove them. In this case, my gene name looks all right here. So you see, this all the genes with a name that you can find in this human gene nomenclature committee. So you should have this in here. So this is based on where we're based on. So in this case, remember, you just save this in the MAT file, so you don't have to do that again. So this is the official gene only. You should have two batches. Okay. Any questions for this part, the preparation of those data sets for DE analysis? Okay. All right, so I saved that in my hard drive so I can safely move back to this session here about the random number generator. This function allows you to do a series of number generation. So here I will do 50,000 again. Okay, this is my X. So this tells the program to give me a vector 50,000, okay, by 1. So this is a vector. If you need 10, you can change this value here to make 100. So this will make a matrix 50,000, 100. All the numbers should follow the distribution we just set up. I don't know if you can do histogram for this. The reason I don't want to do it because they're all integers. Right? You generate 50,000, yeah. Yeah, semicolon.
Yeah, what does
It will suppress the printout of X. You will run this program, give X, but it will not show X on the screen. Yeah, just stop to make this faster. So I'm going to try this histogram for X, see whether it will look like this blue, okay? Because we defined the distribution and generated random number from this distribution. When we redo this, rebuild the histogram, it should look like this. Okay, I put this side by side. I hope you can see the similarity between them. All right. Now, your job right now is to define a variable name, not X, but called Y, okay? And this time you also generated like 50,000 random number from negative binomial distribution, but you follow this yellow parameter. So for this yellow parameterized, so the average is 10 and the p-value 0.6. So after that, I will try to plot these two histograms on the same figure and see whether we can do it. So this is the function, the syntax. We generate this 50,000 values, follow that distribution. Now I'm asking you to generate a Y variable and using same function, but different parameters. So you don't have to type everything again. So what you can do is to move your arrow key to up and down to move between the history lines here. So I move to here and change my variable to Y. And then change this to 10 and 6. Okay, that's all we need to do. We'll generate random number from the same family of this distribution, but the parameter for define this distribution are different ones. It was 7 and 0.3, and this time is 10, 0.6. So the shape we will generate should be the different. I don't know if I can do this to plot the two together. I hope it's smart enough. It's not. So I'm going to read the documentation for histogram function and to see how you can put two distributions in the same figure. Okay, so this is something we want to do. All right, so that's what we want to do. So the way they do it to plot the first histogram, and then put a hold on, and then generate the second. Okay, you just plot the first, and then hold on, and draw another one. So that's the function we want to use. So I cannot do this because it only takes these two. I can run this first. Okay, I should have that plot. Yes?
This is a random question.
Yeah.
Does this room allow for lecture screen record that we can
Yeah, I think it is
on
on the. We do have that. Yeah. Yeah. I will find the link and send to you. Yeah. This automatically been recorded somehow. Yeah. Okay. So this is the way I do this two histogram on the same figure, and I run first, then hold on, then run the second. Okay, so this is not the best because they use different bin size. I can do Z, and if Y is this, Z, remember this distribution has 1 and 0.2. Okay, now I plot Z onto the same figure. So basically, that's the way you change the parameter, but not change the family of the distribution, and get a different distribution to generate different sets of the random number, and then you recover the shape of the distribution using histograms, and also plot multiple histograms on the same figure. All right. Now I'm going to write a function or write a script first to hold everything we have already write for this small example using negative binomial to plot these histograms. And next time, so you don't want to type this again. So if you want to reuse those command line, you want to save them into a file. So next time you just run the file or change the parameter a little bit for the later use. Yes, question? Yeah, so this part you can, if you select the layout on the top, you should be able to find there's comment history, and if you want to highlight, check that. You should have that comment history. Yeah.
Temporarily, out of memory,
Oh, really? Your machine out of memory? Which operation you did to cause that? The data. Oh, yeah. And then 2 sessions. You run. Which step? Are you in the?
It just stopped. It's out of memory
And close everything?
Yeah. At least it stopped processing the...
It's still working on that. Do you have this pop-up window? Oh, you already have saved, right?
But I cannot open it. I tried and it's not opening.
Oh.
Should I just delete it?
No, maybe. So you have saved file. This okay. So maybe you just reboot the machine later once we are trying to do the DE analysis.
Okay.
Yeah.
Okay.
Maybe just shut down one of the session and you should be okay.
Okay.
Yeah. Okay. So now we just want to write all this.
So this histogram, it doesn't show you which one is X, which one is Y, which one is Z.
Yeah, the first one, the blue one should be X.
Yeah, should be. But
Yeah,
if
should be.
you
Yeah, so you don't know.
Yeah.
Yeah.
It doesn't
It doesn't show.
show you which one is.
No, you don't have that information.
Yeah.
That's true. Yeah, so you want to save some of these command lines that become your code. So I will copy some of this from the command line and write it to be saved in a file. So if you do edit, so my script, okay, without this space.
On your histogram, you press I don't know how this is called.
Histogram.
This the button that gives you the legend next to the gradient.
This one here.
Yeah. You press.
Yeah, that's good. Yeah, XYZ. Yeah, you click this. Yeah. You can edit it basically. You should be able to change it. See X1. Yeah. Okay, so this will create a file. It's basically a text file, but with extension called .m. So basically that's M MATLAB function file or MATLAB script file. You want to create this empty file. The reason is you want to save what you already typed in command line, so you can reuse that before. So you know, okay, this is a valuable code here, my function, and that's my second, and this causes error, so I don't want to. So make some edit. Then I know this hold on will work. I will remove this line to the top, copy that, then hold and plot this X, Y, Z. Hold off. And also I want to add a function called figure, and this will create a new figures rather than write on the old figures. So what I did, I just copy what I already had in the command line history window and did some editing. And I can save this. In that case, you should be able to see a new file created in this working folder. So that's your current script. And that's your source code. Okay, you want to rerun this. For example, you close this, and then you can double-click to open it, and then click this run to create this plot. Okay.
When you open your My script, was it not blank?
It's blank.
And then, so you paste it.
Yeah, you copy and paste your code in. Yeah.
No, you just click. Oh, oh, you just. Oh,
So you already paste in here, and then you can save it. Yeah, that's all. You are done. Yeah. So next time you can click and come back, and you can shut down. Yeah, for this. Yeah. Mhm. Yeah, already saved, I believe. Yeah, it's inside here. Yeah. Mhm. So that's the way you organize your source code and put in the script files, and then reuse them by copy around and maybe reorganize in them into different name, put in different folder, and this is for function to draw histogram from negative binomial by changing the parameters. And the next piece of code is to do something like this. When you build this long enough, you should have your own library, and this library is your functional package, so you can use this for later. Okay. Yes, question, Victoria?
And also, you can use the percentage sign on top to
To annotate. Yeah, that's right. So that's a good technology. So you put a percentage sign, these are the comments. Okay. So what this is, so something like that. So you can put. So those comments will not be part of the execution of the code, not to do nothing. It's just there for you to remember what they are. But other than that, this code will run, and if you put a typo, for example, here I put a wrong function name. If I run that again, I should receive error message. Okay, on my script line 3, I have an unknown function which cannot be found anywhere in the pathway in MATLAB. So this unknown function, unless you redefine a function for yourself. So this is not a standard function, so it give you error message. Now I want to write a script. So script and function are not so much different. And this function allow you to change the parameters, script or everything fixed. But now I want to write a function called my simulator. Okay. So you want to simulate. So this is empty. You want to simulate a single cell RNA-seq gene. Okay, so you want to generate X. So this X looks like something like 1, 0, 2, 3, 4, 0, 0. Something looks like this. Okay. Basically, you want to simulate one gene's expression. You can do this by using non-negative binomial random number generator. But you need a parameter, so parameter 1. You need parameter 2, which is the p-value, the success rate. You need two numbers. This number hasn't been defined yet. So you need to give this parameter 1, parameter 2 to define this. And also you need to know how many cells, number of cells. So basically, you need 3 numbers to run this, and 1. So because you only generate the data for 1 gene. Okay, let's put the gene in the row. So this is not a script. This is a framework of a function. So I'm ready to put the 3 values to replace those variables in order to generate a gene expression. So for example, I can put 6 and here 0.05. And the number of cells I want to generate is 500. Now this is a script. So you run it, you will generate X and saved into the workspace. So what do you think about this value, the random number you generated? It looks like a real single-cell expression gene. So I really want to have more zeros. I don't know how to change the parameter to give more zeros. I don't know. So I try maybe put this really small, run this program again. Well, this is wrong direction probably. So I will give larger p-value to generate this. It looks better. And I will make this smaller, say 3. Okay? So I can adjust those parameters until I believe, okay, this looks like a real single-cell gene. Okay. Now I want to do is to not predefine those values, not 3, not 0.5, not 500, but make them more flexible. So that's why I'm going to define a function instead of using a fixed value in the script. This function will give you X, the output, and my input, the name should be the same as my file, so simulator. And I need 3 parameters. 2 and number cells. So I comment them out because I don't need them to be a fixed value. Instead, I need your input when you use this function to define your own parameter 1, parameter 2, and how many cells you want to generate this gene expression for those cells. So in this way, we define a function, and instead of to just script, this function will be more useful, more general in general sense. You can change parameter into the value you want. So how can I run this? Now I cannot run this directly from this as a script because those values hasn't been defined yet. What I should do is from the outside to call it. Okay, I should call x, call this function simulator, and give definition of the 3, 0.6, and 4,000 cells. Now you have your own simulator to simulate one gene's expression using the parameter you preset. Okay, you can easily change this to different values to generate different genes expression values. Okay, so that's how you use a function you define. So in real application, when you want to generate a gene, so this is just one gene, you don't want to generate the same gene value again and again, so because gene has different values of the expression level. So sometimes you want to generate x1 is this level, but x2 maybe higher expression. In that case, you have to change those values. Okay? But how you set up those values? You don't want to manually set, okay, for gene 1 I use this, gene 2 I type different. This will take time. So I will use another random number generator to generate those numbers. Okay, so this is one layer of function, generate random numbers, and those random numbers will put in your simulator to generate those. So just like a hierarchy, you have a nested function. Those function generate those key parameter values, and each time you put the parameter values into this function to generate the real data, and then you loop that again and again. All right, those random number generator to create a whole matrix. All right, okay. We need to take 5 minutes break. Please come back in at 11:06. Okay, so far I hope you understand the difference between MATLAB script and the function. So script, I would say, is basically for yourself, and you test your code and to see whether in some special case your algorithm or your method works fine. And the function is more generalized. You not predefine any concrete values, but give the option for yourself later or for other users to use your function. They can set up different parameters to achieve the purpose the function want to give to them. This toolbox contains a lot of functions, so I wrote those functions. So you can call them, or I call from the interface, but every step is one function after another, one function after another. So I'm going to show you the latest, this simulator built in the toolbox. Let's see. So if I don't do anything, in this case, I don't load example data, it is cancel. So you still have this. All the menus are disabled, except those in help, and also there are 3 items you can select in the file. The one of these is simulate data. Okay, I use a method published in this PubMed paper. In this case, you will be asked how many genes, how many cells you want to simulate. And then once you click OK, the program will just run a simulator function, which is very similar to what you see on this example. And that's your generated. Okay, and there's no name. It's just gene 1, gene 2. You can output this matrix. We can take a look what the X matrix looks like, but genes is just G1, G2. Okay, everything is simulated. So we can open the X matrix to look the data generated. Okay. You see some of the genes looks higher with higher expression level compared to another. So 16 seems to have a higher expression, while 13 maybe a lower expression. They all randomly generated, but it's set up by some predefined parameters to define the shape of distribution of the average. Okay, we can take a look of the function. So this is your toy example simulator, but I want you to do edit, where I put it, simulate data. So this is a real data function. You should be able to find this function inside this toolbox. So the data you see here generated through this interface goes through this, okay, this function. As you can see, this function will take first how many genes and how many cells you want to simulate. And it will give you a matrix rather than just one gene. And then there are 2 different types of methods. One of these is the one I cite in the PubMed ID. This is called a simple. So this is three parameters. If you don't give anything, then they automatically give you 500, 1,000 by default. Then I predefine the X matrix as a full zeros. Okay, so this function just create matrix based on your definition of the dimension. So how many rows, how many columns, and I put a 0 there. I just pre-allocate a memory in the computer to predefine those values. Then I will start to fill that in. So if you select the simple method, then you have a parameter called shape, and then the scaling factor 0.5. These two will generate a list of random number using gamma distribution random generator. So we learned uniformly distributed, normal distribution, and negative binomial. Here is just called a gamma random number generator. So it follows a gamma distribution. The characteristics of gamma distribution is the shape change drastically based on the small change of your shape and the scaling factor. So that gives you a broad type of the average. So I create number of genes average. Okay, so for each gene, I go through, use one of this predefined average and put into negative binomial, just R. So R is predefined by beta distribution. Sometimes it's 20, sometimes it's 1, so it changes greatly. And then this second value is fixed. In that way, I simulate for that particular gene for given parameter average, then you generate that particular gene's expression for that many of the cells. It's very simple and also very effective. Okay, you can use this to generate. So another method is called, this uses first author's surname to name this method. Similar, so here you have that, and you have a random number. Yeah, that's very similar. Okay. All right, so now we should look at the next. So I hope we finished the top 5 already here. So next we should have to learn how to compute the average, the mean, the standard deviation, and the CV, okay? So mean is the built-in function. If you give a single number, the average should be itself. If you give a vector 0.45, it computes the mean for this vector, either row and. If you gave a matrix, okay, this is my matrix. In this case, you have to tell the mean function whether you want to compute the mean by column or by the rows. So this should be by column. Then if you do 2, you got by mean, okay? So many functions in descriptive statistics in MATLAB, you have to give this direction. So you want to do, if you have an input is a matrix, whether you want to compute by columns or by rows, column-wise, row-wise, make a difference. Okay, you want to compute the variance. So we can just use this example. So to compute the variance for the matrix of A, so A is a 3 by 3 matrix. Then this variance, if you do direction of 1, that's by default in this way, okay? The same as this. If you want to do it by rows, you have to put here. There's another parameter in the middle. That parameter is called the called W. So whether well, this vector is indicator 0, 1. Okay. To let you to, when you compute the variance, whether you will divide by n or divide by n1 minus 1. Make a slightly difference. So don't worry about the middle one. So you can put a 0 here, okay? By default. Okay, for example, you have A, then you can define the mean. Let's see. U is its mean. We're doing this by columns, okay? Then you can build, see, V, it's C, its variance, okay? Again, it's by row, so treat them by like 3 variables. And the CV is mean divided by variance. That's definition we mentioned. I double check. So it's not a variance, it's a standard deviation divided by mean, okay? So we need to compute not a variance, but the standard deviation, STD. So CV is S divided by the mean. So this dot may be essential. I don't know. The new feature of this language probably allow you to do this even without this dot. I'm not so sure whether you can do this or not. It's not. So that means slightly different thing, okay? So you need to put a dot in there. Dot means element by element. So you have a standard deviation, have 3 numbers. The 3 numbers will divide by corresponding mean for those 3 numbers. Yeah. Which function?
With dot as well as without dot.
Oh, without dot means the division between 2 matrices. So you know when you multiplicate one matrix with another, it's very different operation from you multiplicate every element with another element. So the same thing here. The division is, if you without that dot means one matrix divided by another matrix. If you put a dot, that means by element, one element divided by corresponding another element, the same position in another matrix. So in our case, we should put the dot here in order to compute CV, okay? So we can simulate a matrix using this simple algorithm to create a simulated dataset X. Now I want you to compute this 500 genes average, and then compute this 500 genes CV. And then we are going to plot a scatter plot to look at this 500 genes mean and the CV's relationship. So x-axis will be the mean and y-axis will be the CV. And each genes have 2 values and put in this scatter plot, see what they look like. Remember, you use this compute a mean, this by column. That's not what we want. Because by column, you are computing the average of expression per cell. So we are going to do by rows, the 500 genes. So what you need to do is to put a 2 here, okay? So that's your U vector. Let's do standard deviation for X. Also put 0 here, 2 here. So this is by rows. And the second is indicator, say whether when compute the variance should it divide by n or n minus 1. Okay, you know how to compute the CVs using this. Now you have an average, tells you the center of those expression of that particular gene across the sample, 1,000 cells. And you also have idea about their variability, so how variable this gene changed using this CV as an indicator. Larger CV means this huge variation against the mean. So we are going to do a scatter plot. This won't be good looking because the values will be really skewed in the scatter. And we will do log later, okay? You have a mu here as x-axis and the CV here. Remember, they are the same numbers by pair, 500 by 500. This should be, if I gave a figure here first, all right, so this means if this gene have a high average, then the CV should be lower. So you see this negative trend. Is that okay? We can do a log transformation. So log, we use nature log here. And then you get this straight line basically. So that's what I described in the lecture in that particular page, this slide. So you do this transformation, then you get a straight line. That's because of distribution to guarantee you have this relationship. So log is to, okay. Then you need to put, I want to put a dot here. So log is another scatter plot format function, and basically doing the same as you do scatter plot, log your input first. But this one allows you to directly put those variables without transformation, but still the axis is in the log format. We are using the simulated data, so everything looks great. But when you plug in real data, and you will see some gene jump off from this curve, okay? They always jump to top. I never seen any gene go down. There's only one Nature paper, see. The observed distribution of the gene expression at the single cell level is so-called Saber person, and in that case, some genes jump down this curve. In my single cell data analysis, I never see any gene jump down and all the genes up. Those are the biological variability. It's really the noise in the expression created by the activity of gene itself. It's 500 cells simulated. Yeah.
You run them for the first 500?
Yeah, we simulate the 500 genes. In this case, we simulate in this function. In this function, we generate an X matrix is 500 by 1,000. Yeah, 1,000 cells. And, yeah, X is a matrix. So this function will give you the covariance matrix. This should be 500 by 500. So yeah, so we have to transpose data maybe. So this function will consider rows as a cell and column as a gene. So in order to get the correct covariance matrix between genes, we have to transpose our input matrix to make it cell by gene, and this function will compute for the genes. So C is a covariance matrix between those 5 genes expression profile in those 1,000 cells. So I will see this will be the xt transposed x. Okay, it was gene by cell and transposed and renamed it to xt. So the covariance should compute with this transformed, and that's our C, okay? So in the diagonal position, those will be the variance of each gene. So the first value, 87.8824, should be the variance of the first gene. Remember, we have first column. So this value should be this, okay? And then 24.94 should be the second gene's variance. All right? And the covariance, which is between genes, so gene 1 against gene 2, gene 1 against 3, so there's a pairwise. That's the covariance between one gene against another. So this value here, for example, negative 0.75 should be the covariance you compute between the first T, the first gene, with xt, the second gene. It gives this whole matrix. So this large C table that's pairwise, one gene against another. The sign of those positive negative tells you whether they co-expressed or anti-correlated. So give you some idea about those. So this too will take much longer to explain clearly. So I will leave for the for this two maybe in the lecture and give sometime in next week. But now we can go to the DE analysis for your data. Okay? Any questions before we move to differential expression analysis? Yes? The covariance matrix. Mm-hmm. So this C is computed using this function. This function will take, you have 500 genes, it will take first gene against another, first gene against third, and second gene against third, second gene against fourth. So they do this pairwise. So that's, you have a huge matrix. That's 500 by 500. We probably have a way to show this. I don't know whether we can see the color of this. Hard to see. Maybe do a transformation. Yeah, I don't know. Yeah, but it's hard to see the values, but you see, okay, there. They're symmetric, okay? If you look at those values. Okay, I'm come back to this example here. I'll do some QC quickly, so I will remove some genes, I believe. Just make the data a little bit smaller, so otherwise each step take a long time to finish. So the first concept is we do have this cells from two conditions. We don't want to do direct comparison because we want to do cell type specific. So you don't want to do all the cells from here against and all the cells there. Because that doesn't make sense. That's a bulk RNA-seq. You don't separate the cell, different cell type. So we need to be cell type specific. So in this case, we need to know what cell types are in there. Okay? So I will check those cell types. I don't know how many years. I have 11 or 12 cell types. You certainly can rotate and look at them, and also remember last time I showed you, you can have this multi-group view to see cell type and batch ID at the same time. So you know this, right, everybody? No? I think. Yeah, last time I showed you, and for example, in this view, you can see, okay, this large group, this part, they all from another condition, and they are keratinocytes. So this is like a surface skin cell. And this part I highlighted from the same side here, from the condition 2. And now I can see, okay, this part, fibroblasts are from this condition. So you can basically brush them and see which part to highlight from this part and compare to this part. Are we okay? Are we doing this visual comparison, contrast? Then you want to do some statistics. See, for any given cell type, is this much of those cell type from one condition or another? So we need another view, which is this one here. This gave you the so-called cross table. So also we're interested in the batch ID and the cell type. And we will get 2 different ways to organize this. You want to use both, maybe. It will give you this distribution. Okay, let's look at this first. This separates cells by cell type. So we have a keratinocytes most, okay, in our, how many cells in total? Over 17,000 cells. Majority of them from this group. And the fibroblasts in the second place. So the top panel gives you the total number of each category. And then these 2 colors indicate how many cells from blue group, how many cells from the red group. So give you the portion. And the portion even clear here, because here is the percentage of cells stretched for each cell type. Okay, now you have some ideas. See, the pancreatic stellate cell looks only appeared in blue samples. However, it's not very important because there's just a couple of them, right? So there's no major proportional. There's some proportional change, but not the number of cells. So this could be completely by random assignment or some other factors. So it won't be the major change. But I see the second difference maybe in the fibroblasts, the 50-50, almost half-half. Endothelium cell, the same. So dendritic cell looks like we have more in the blue group, and the basal cell more. And also the total number of those cells are also decent numbers. So they're not so low. You still have hundreds, maybe several thousands of them. So I would think this may be some of the proportions of abundance change in terms of the cell, particular cell type between these 2 samples. If you can rule out maybe the sampling procedure gave you the bias, maybe through another replicates, another set of those. And also you see the same change of this ratio, then you probably can see, okay, there's some cell type abundance difference between these 2 samples. If you want to do statistics, there's chi-square test or goodness of fit. So there's another statistic test for the proportions. A different view, this is based on grouped by sample. So you have two samples, then you see this sample on the left have more cells collected or sequenced than this sample. And within this, we group them by different cell types, and you see the change. And here, again, it's scaled by the percentage. Okay? Any questions? Well, we are doing the comparison. Yes?
I got lost on how we got here.
You see here?
I got lost from the.
She got lost.
Oh, got lost. So on your left is the first sample with this ID 449, and that indicates how many cells in that sample. So this is over 10,000 cells. And the right side is how many cells, how high this bar is, how many cells from there. And it also tells you within those cells, those different types of cells, like this light green is carnitine sites, and the second, this light blue green are the fibroblasts. So it tells you what cell types in that sample as well. It's almost the same information, but it's just organized in different way. Okay, so you should do by both. So the same information, just organized in different ways, either separated by the cell type first or cell separated by the samples. Next thing you want to do is to click this button maybe. This will help you to separate each cell type independently. So we have 11, so maybe we want to extract top 5 cell types and process them independently. We are not going to compare all against all, because that's the mix of the different cell type doesn't make any sense eventually. So we need this button to separate individual cell type. You click a cell type, and it will prepare a list of cell types, and also ordered by the number of cells in each group. Then you can decide, I want this top 5, the most abundant cell types, to be extracted and make the separated view. I hope you are not running into the memory issue, because this is not a small data set, by the way. So after you extract the particular cell type later, then you can decide, I want to focus on this one, then you can compare between 2 samples. So I'm going to use my laptop example to show you, but it's the same procedure. And then, as I said, you can use this button to separate the cells, to extract them. Oh, I can do this now. Let me switch it back. So again, I can finish the extraction of cells. Okay, in here, this subset of the cell separated by the cell type is ordered by the number of cells. So you have 8,000 cells here, so it's on the top, the second, the third. So then you can click this finger. Say I want to extract 1, 2, 3, 4. Maybe we try first for majority of a cell type. Let me switch off some of others. So I click this button. See, I want to select. I'll do top 2 maybe. Okay, this is extract cell. I know this is a fibroblast. If you look at the cell type, it should be only have fibroblast here. And you want to do a QC on this again. Just get rid of some of those cells, which some genes is almost empty. There's no meaning to compare between 2 samples. So once you are ready, everything you do in this window will be fibroblast cell type specific. And you can show the difference between these 2 batches. Okay, I want to compare between them. Which button here? The menu will be the 2, and then have a DE analysis. Or you can click this button here. This is for compare the difference of gene expression between these 2 samples. You want to compare that between batch IDs. You don't want to compare between cell types because there's only one cell type. There's no way you can compare. So you compare batch IDs between these 2 samples. That's 2 samples you want to select. Okay, sometimes you have 3 batches. You have to select 2 of them to compare pairwisely. In this case, we only have 2 samples, so you select them, and you use one of these tests. And these 2 require R installed, and you have to use a package installed. So we just use this one to compare basically the medium between 2 samples. This will work cross genes, one gene by another. Treat all the genes independently. At the end, you will generate a table. This table contains all the genes. So I can put this table saved to in workspace. If you want to save into Word, Excel, you can. So this table called TD gene list, and it's there. So after that, the program will ask you, do you want to, from that table, extract upregulated